Section 30.4 Numerical Differentiation Finite Difference Formulas. The derivative of f at x0 is defined as in this equation. This formula gives an obvious way to generate an approximation of f prime at x0. The quotient is approaching the derivative as h approaches 0. So the quotient itself will be a good approximation of the derivative when h is small. Now let's see 2-point difference formulas. Here we consider 2 points x0 and x1. x1 is x0 plus h. So pictorially we have here that is x0 and that is x1. Now here y equal fx is given in this way. Then here we try to estimate the derivative at x0 and at x1. Now it is related with the first Lagrange polynomial, which means that line passing these 2 points. Okay, let's try to draw the first Lagrange polynomial. Okay, there's a line. Oops, here. Okay. Yeah, that line. Okay. Now we call this line P01. It's a polynomial passing x0 and x1. Okay. Then from polynomial interpolation error theorem, we have error term. Now practically P01 can be written explicitly in this way. This is L10, this is L11. Now we differentiate the equation, then we can get the following equation. F prime at x is the same as, now from this term we have 1 over minus h times f of x0. That is this one. Now there is 1 over h f of x1. That is this one. So from this one we can get that one. Now for this product, first we differentiate this one to get this one. And now we differentiate it. We have this one. The xi is dependent on x, so that here this derivative cannot be 0. Xi is not a constant. Okay. Now, from this equation, we try to evaluate the f prime, the derivative at x0 and x1. So if we are using x0, then this term, and here we have this one, but for this one, once x equal x0, then this will be 0. Of course, when x is x1, also it will be 0. So that here, when x is x1, we have the remainder in this form, but we have the same difference formula. But that one is now the formula looking from x0, from left end point. In the case, the error is given in here, and once we try to look at the formula from right end point, then error is given in this way. Now for general xi, now when h is positive, xi plus h will be a fourth point. So at xi, this quotient is a finite difference formula using fourth point. So we call this the fourth difference formula. And we try to use the notation here, and x directional derivative difference formula along with the fourth point of f at xi. Similarly, we can define the backward difference formula. Now at xi minus h is backward point, so that this quotient is using a backward point, so that we call it the backward difference formula, and we are using this notation, x directional difference using backward point for function f at xi. Okay, that's the two difference formulas. Okay. Now we'll test the accuracy, particularly the fourth difference formula. Use the fourth difference formula to approximate f of x equals x cubed at x0 equals 1 using h here, 3 different h, and each time halved. Okay, here f is defined. This is a maple language. Defined, and x0 is 1. Now h is 0.1. Now we are measuring the fourth difference. Then it is now 3.31. Here f prime at 1, okay, f prime is 3x squared. At 1, the true value is 3. So that after decimal point, 0.31 is the error. Now h is halved, then we have that result from the quotient. And one more time, for halved h, the quotient gives this result. You can easily see that the error is halved from the previous one. Again, halved from previous one, not exactly half, however, asymptotically half. Okay, so that means that it is first order. Okay. In general, once we start with, rather than 2 points, start with just n plus 1 distinct points, then the interpolation error theorem read in this way. We already know that from the interpolation error theorem. Now, if we differentiate, then we can get here f prime equals, okay, for this term, for these cardinal functions, we have here derivative. And now for this product, we first differentiate this one and multiply this, and then we put here, and for the second one, we get the derivative of this second term. Now here we try to evaluate at xi, here the nodal points, and one of them here. In fact, for every xi, we can evaluate. Then, now rather than x, we put xi. Then for that one, because of this whole product, this will disappear. And then from this one will make a n term summation. So among them, only one will survive, so that it is simplified in this way. So that here, f prime at xi for every I, that's the n plus 1 point difference formula, and this is the remainder, the error. So this term is, once it's small, this error is small, then this formula will approximate the derivative at xi quite accurately. Anyway, this is the n plus first point, n plus 1 point difference formula. Okay. Let's see example 3-point difference formula. Here n equal 2. So for convenience, we choose x0. x1 is h moved to the right. x2 is again h moved. Then we can construct the second order cardinal basis functions. And here L20, L21, L22. And from the polynomial interpolation error theorem we have here, that is second order Lagrange polynomial, and this is the error term. Okay, now we try to get derivative, then f prime is now derivative of these cardinal functions and derivative of the remainder. And we try to evaluate here at each point x0, x1, x2. Once we try to evaluate at x0, then also, because it's product, and it'll be simplified. And if you go detail, try to compute the detail, then you can reach at this one. Now, here also, here these cardinal functions are explicitly constructed, and you can differentiate these functions, and then you can evaluate at x0. Then after doing some algebra, you can reach at this term from these three terms, and then this will be simplified into this one. Now, exactly same way, after differentiation, you can evaluate at x1, and then you can get this formula from the three terms, and from the error, the remainder term, you will have such error. And also for x2, right endpoint, you can get from this one, here this one, and then this is the error. Here for 3-point formula, that is left endpoint formula. This is a midpoint formula. This is right end point formula. So we got the second order formulas by using 3 points. Okay. Now, exactly same way, we can get 5-point difference formulas. Start with 5 points, and here try to make fourth order Lagrange polynomial, and along with the corresponding remainder. And then we differentiate the equation, and then try to evaluate at each point. Then you can get a formula. We'll not go to the detail, but here we have this one. F prime at x0 by using 5-point difference formula, we get that one. That is now x0 is a midpoint, and f minus 2 means f at x0 minus 2h. And there's a f sub minus 1 means x0 minus h. There is a f at x0 plus h. There's f at x0 plus 2h. So yeah, this is a 5-point formula, and x0 is the midpoint. So this is the midpoint formula, and error is fourth order. Now for that one, here f0, f1, f2, f3, f4. So f0 is left endpoint. So this is left endpoint formula, and we have that formula again. The error is given in this way. Looks like larger than this error. However, yet this is fourth order. Okay, and in this way, by using more point involved, you can get high order difference formulas. In general, in numerical differentiation, we have these results. Once a given function is now interpolated by using nth order polynomial, and we have remainder term, then the remainder term is order h to the n plus 1, because P of n is using n plus 1 points. Okay. Now once you make a derivative, then now this derivative, the approximation, has now h to the n order accuracy. So accuracy is order is 1 down. And if you try to also approximate f double prime from polynomial double prime, the interpolating polynomial double prime, then again one more time here the power go down. So we can see here from the above summary that for f double prime, 3-point formula in the case n is 2, and so that its accuracy is order h. And for 5-point formula, in the case n is 4, its accuracy is order h cubed. Now, that's the theory, and this result holds for every point in the interval x0 to xn, including all nodal point xi. In fact, every point between the beginning point and the end point. And so that here for second derivative, if we are using 3-point formula, then only the accuracy is order h. However, if you try to get formula for midpoint, then you can enjoy a high order accuracy. So that one, for example, this is true for every point x0, x1, x2. But if we are focusing on the midpoint x1, then here we can get the second order for second derivative. That we'll see the possibility. We start with a recall for Taylor's theorem with a Lagrange remainder. Okay, that is the theorem 3.34. Early we studied, and that is now the given function is sufficiently differentiable, then for every x in the interval we have that is nth order polynomial plus now Rn, which is one term. That is a Taylor theorem. Now from the theorem, rather than x, we are using x0 plus h. x0 is the center of this formula, and x is ideally around x0. So rather than x, we try to use x0 plus h. So x0 plus h will be around x0. Once h is positive, then it will be right side of x0. H is negative, then it is the left-hand side of x0. So rather than x, we try to use x0 plus h. Then here, so they are replacing x by x0 h in the Taylor theorem. We have this formula. And in detail, we can write this one. Rather than sigma notation, we write down explicitly details. Then we have that, and here that is R and H here. Okay, we'll use this explicit formula to get the midpoint formula for f double prime. Here in this example, use the Taylor series to derive the midpoint formula for f double prime at x0. So we are using x0 and x0 minus h and x0 plus h, and this combination will make here a formula, and then error is second order, fourth order, sixth order, and so on. So the overall over there is second order. Okay, then we can get this formula quite easily, and we are using this formula. F x0h is given here exactly the same. Now x0 minus h, that is, rather than plus h, we are using minus h, so that here negative is appearing. The minus h squared is h squared, so we have a plus, and again cubed, so we have a minus, and fourth power plus, and so on. Now here the purpose of this computation is we want to get f double prime x0 is something, so that now we want to eliminate this term. We want to eliminate basically this term and also that term, and by adding two equations, then plus minus, it'll disappear, and also that will disappear. And here left hand side is addition, right hand side is twice of this one, and again twice of that one, again twice of that one, and so on. Now we solve for f double prime x0. We move this one to the other side, also that on the other side, and divide by h squared. Then we'll have this one. So by using Taylor series expansion, we can get such a midpoint formula, and that will be higher, one order higher than the basic theory. So it's quite useful. Here, the higher order accuracy in this equation can be achieved at the midpoint only. Once you are trying to get the formula for left endpoint, right endpoint, then you follow the basic theory. That means you can get only first order convergence, first order error. But for this midpoint formula, we have now second order error. Okay. Okay, let's see this example. Use the second derivative midpoint formula to approximate f double prime 1 for f of x is given to be x to the 5 minus 3x squared, using h is now 0.2, 0.1, and 0.05. Again, and we will try to use symbolic tool maple, and f is defined and x0 is 1. Now, after second derivative, we try to evaluate at x0, then the true value is 14. From this one, in fact, f prime is same as now 5x to the 4 minus 6x, and one more time f double prime equal 20x squared minus x. Once x equal 1, then the value, okay, so here x is 1, then value is 14. So we have the true value 14. Now we are testing the accuracy of the second derivative midpoint formula. Yeah, that one. So f of x0, there's a f of x0 minus h, f of x0 plus h, combination divided by h squared. That is exactly this formula. Okay. Okay. Now h is 0.2. We have that one. So that again, after decimal point, this is the error. With h is 0.1, we have error, and again, with h halved, we have such error. As you can see here, the error become quarter when h is halved. That means the error converges in second order. Okay. Okay, that's the end of section. Thank you.